Right. So in the previous video, I have shown you how to detect multicollinearity and two of the methods which are widely popular in the literature, and one of them is, as you know, variance inflation factors or VIF, and the second being condition indices. In this case, a linear model would not suffice, and we need different or penalized forms of regression. So we'll be looking at one of those in ridge regression, and a ridge regression is the L2 norm of the standard regression, such as like beta j square, right? And the usual in the after the matrix notation, you apply a penalty parameter in lambda, and then you do a L2 norm, L2 norm um, of beta j, right? So let's get started without any further ado. And before we start, let's just remove all the variables so it's we can create new ones. Anyway, we'll be working with the same data set as before, the ISLR data sets, and the data being hitters about the baseball players in whatever in some American leagues. Anyway, so just like before, model dot matrix. This means we want all the rows but remove the first column, and the first column is the intercept. So I'll just write it down. It's the same approach like previously, and we're going to make a like a response variable as well, and that would be our salary variable, and that would be yes. And NA exclude is very self-explanatory, I hope, and it removes all the NA values. So yeah, so that so the ideal lambda parameter is obtained by a cross-validation search, by an n-fold cross-validation search. So we're just going to set up a grid of, let's, like, this can be arbitrary. Okay, there is no standard practice in the literature that you must abide by. So it's, but make sure that it's exhaustive. So all of these options are evaluated, and then you can find your ideal uh, penalty parameter. Anyway, so here we are doing a grid of from 10 raised to 10 to 10 raised to minus 2. Oops, made an error here. Cool. And the length of it would be, as you can see here, 100. Fantastic. Okay. So we can fit in a ridge model, and that can be done by um, the library jlmnet. If you do not have that library, I just suggest that you install packages and write down the name. Okay, cool. So let's just run that, and jlmnet x y. Here alpha value indicates, like, if it's 0, it's implied that the fit would be a ridge model. If it was 1, it would have been a lasso, and the values between 0 and 1 indicate that it's an elastic net, which is a compromise between ridge and lasso. Fantastic. Lambda is the penalty parameter. We'll just set it to grid. And one thing that we have to standardize these variables, because as you know that the beta hat ridge, let's say beta hat r, is not an unbiased estimator of beta, unlike the what we had in the least square model. It is not it is not a unbiased estimator for that. So first we have to standardize the variables, so it fits our assumptions about the linear models, such as the errors are distributed normally and with the variance of the standard normal distributions. Anyway, so we'll just like check out the dimensions of coefficients. Ridge. Okay, let's just first run these. As you can see, there is the dimensions you can see here of the ridge model. and we can check the coefficients of the model as well. So these are the sparse matrix coefficients. Is again the notation means all the rows and these many columns. Okay. So in order to calculate an L2 norm, okay, L2 norm, we have to find the best penalty parameter in order to make predictions. Okay, so we can do by set seed, and this is nothing, this is to ensure reproducibility. Okay, so when you run this piece of code again, you'll obtain the same results. So it's like pseudo normal, it generates pseudo random numbers, right? So we can just like write reg cv, just like this, some random name, cv dot, okay, we can select what fold cross validation we need to do. We'll just stick to its default is I think 10 if I'm not mistaken, so we are going to just stick with that. Awesome. And we'll find out what the mm, let me just store it into a variable. So best lambda or best penalty parameter in this case would be reg cv lambda min. So we can just see what the best lambda here is. So as you can see, it suggests by this, the cv method suggests like we fit in the lambda 6.135 whatever into our predictions. So yeah, so we are going to do just that. So my prediction is sorry this is our original design matrix. We can, as you know, mean squared error can be found out between yi and y minus yi square. So we can just like do this. Just, the original y, which is our response, and the predicted values, the square of it. We can just check what the MSE is then. Oh, my bad. Yeah. So as you can see, the mean squared error is minimized at 93971. And for s is equal to 0, let me just put in a note here. If s equal to 0, our beta hat reg is equal to beta hat obtained by least square method. Okay, so it's if s like or lambda is equal to 0, there is no difference between the two. As you can, if you see the definition or the formulae, it's the lambda is multiplied by the L2 norm here, so it becomes 0. That will give you the same old result as the least square method. Okay, so we can also do some predictions based on that, and we can do this by the predict function, right? We can predict the coefficients. Yes, you can just select the best lambda. Okay, my bad. Okay. So yeah, this is what you get. And before I end this video, let me just put a caveat here. Like reg is the problem, or the drawback of reg is it will never tell you, it is not very conducive if you want to do variable selection. So now as you can see there, the coefficients that we obtained by the ridge regression have no zero terms, right? So every regressor term holds a value, okay, which is not ideal, because we'd like to follow the principle of parsimony as when we try to fit models. So this is dealt by lasso regression and lasso fit. So this is the drawback of the ridge model. Yeah. So I hope you like this one, and see you in the next one. Bye bye.